Assalamualaikum. Now we will be presenting about application of Fourier transform in electrical engineering and other field, which is optic. So here presented by Nur Akila, Nur Adila, Maizatul Ashikin, Azmira Najwa, and Raudatul Nazira. So I will start first for our presentation about Fourier transform. Next slide, please. This is introduction of Fourier transform. First, mathematical method to function in the amplitude vs time domain to the amplitude vs frequency domain for non-periodic function. Second is Fourier transform decompose a signal into its frequency components. Third, periodic signal can be analyzed either by using Fourier series or Fourier transform. So here, the term of Fourier transform refer to both the frequency domain representation and the mathematical operation that associate the frequency domain representation to a function of time. The Fourier transform is not limited to a function of time, but the domain of the original function is commonly referred as the time domain. There is also an inverse Fourier transform that mathematically function from frequency domain representation, as the proven by Fourier transform. Next slide, please. This is waveform of periodic function and non-periodic function. For example, there a rectangular pulse range where a periodic function about vertical axis ft that we call a Fourier series. While the t is period, the amplitude is time domain. And we get the amplitude to the frequency domain for the Fourier series. So for the Fourier transform is about a signal path range. This is, I want to find the versus time. There, the main function of Fourier transform. When we draw a line to the right signal path range about amplitude, this value that we take the same series with the sine wave for the Fourier series, and it also becomes the same sine wave and Fourier transform with Fourier frequency omega instead the amplitude versus frequency. Next slide. Okay, now I will pass to next presenter, Azmira Najwa.
Okay, thank you, Akila. Hi, my name is Azmira Najwa binti Syaril. I will present about application Fourier transform in electrical engineering. Fourier transform have many applications. Mainly, it converts time domain signal to frequency domain signal, at which signal can be analyzed. Fourier transform help to analyze spectrum of the signal, help in find the response of continuous time Fourier transform is for analog signal and discrete time Fourier transform is for discrete signal. Discrete Fourier transform are helpful in digital signal processing for making convolution and many other signal manipulation. As a tool for this application is used in almost all field science and engineering. In electrical engineering, the Fourier method is found in all types of signal processing from communication and circuit design to imaging and optics. Last, the Fourier transform as a tool to solve physical problems. Next, I will pass to Nur Adila.
Okay, thank you, Azmira.
Now I will explain about application Fourier transform. Have two applications Fourier transform, which is first continuous Fourier transform and second discrete Fourier transform. This continuous Fourier transform have formula. T is continuous time index in second. Omega is continuous frequency index in radian per second. And then this is formula inverse transform. Okay, next discrete Fourier transform. This is that formula. W is discrete radian frequency, N is discrete time index in samples, and K is discrete frequency index in beam, and the last frequency radian relationship. Okay, next slide. Now in this slide, I want to explain the calculation example 1 based on formula continuously Fourier transform. So, this is signal path range for a Fourier transform function. That formula is given for this example as W x omega integrate by xt exponent to the power of negative j omega t dt. So, first we put integrate of negative a to the a and x equal to the 1 multiplied by negative j omega t dt. And then we integrate 2 divided by 2 j omega. And the final answer we get 2a multiplied by sine omega a. Okay, next slide. Okay, then we plot the graph. We get the waveform like this. Okay. Okay, then next slide I will pass by presented now Raudato Nazira.
Assalamualaikum warahmatullahi wabarakatuh. Thank you, Adila. I will present about the application of Fourier transform in optics. The first one, Fourier optics is used in the field of optical information processing. Some properties of a lens provide numerous applications in optical signal processing, such as spatial filtering, optical correlation, generated holograms. Fourier optical theory is used in interferometry, optical tweezers, atom traps, and quantum computing. Optics are used to reconstruct the phase of light intensity in the spatial frequency plane. Okay, next slide. Okay, this is the calculation of Fourier transform in optics in diffraction. This is a rectangular aperture characterized by the transmittance function fxy equal to I for x in between negative a2 and a2 between negative b2 and b2, where the xy plane is the plane of the aperture. The intensity distribution in the far field diffraction pattern is in the formula where UV are the spatial frequency for the x and y dimensions. The far field diffraction pattern can only be observed at infinity. After the diffracting aperture, the plane at infinity is imaged on the focal plane the lens. Focal plane of the lens. This explains why a lens can perform a Fourier transform. Okay, next, I will pass to the next presenter, Maizatul.
Okay, thank you to Raudato Nazira. Okay, my name is Maizatul Ashiki Miti Azman. Okay, I will present about optical spatial filtering. in the infinite lens limit, it can be shown that the field distribution in the focal plane of the lens is given by, okay, this is the formula for optical spatial filtering. Okay, so S is the object distance, F is the focal length of the lens, so this is the coordinate in the focal plane. Okay, UV is the Fourier transform of the object function. Okay, U is equal to the negative XF divided by lambda F, and V is equal to negative YF divided by lambda F. Okay, the observable intensity pattern in the focal plane of the length, which is E multiplied with XF and YF and divided by 2. And does not depend on the object position. Okay, next. Okay, spatial Fourier transform. So this is the formula. Okay, Fourier coordinate UV have unit of inverse length and are called spatial frequencies. Okay, next, a plane wave of amplitude E naught impinges on the object. Okay, the field distribution immediately behind the object E, which is xy, is equal to fxy time E naught. Okay, the object information is impressed onto the light wave. Okay, lastly, these optical processes can produce the Fourier transform of E, which is x, y, and the object function. Okay, that's all from me and my teammate. Thank you.